Welcome to the fourth lecture in the first week of quantitative methods in chemistry. Let us start by summarizing, or rather comparing, the different units of concentration that we have discussed in this class so far. So, I am going to make a large table, hopefully that is going to help us understand how things go. So, first one is the parameter, next one let us call it units, followed by temperature, density. To understand whether it is independent of measurement of temperature, then we can try to understand how this can be interconverted. Does it require molecular weight? Interconversion. Okay. So, let us keep the basis of everything as molarity, that will help us relate it across different units. So, the units of molarity is capital M, molar, and is it temperature independent? Temp dependent, largely because you have volume in the denominator, which would change as a function of temperature, or rather which could change as a function of temperature. Yes, it requires the molecular weight to be known, to be defined. So, basically molarity is defined as number of moles divided by volume of solution in liters, and this is also given as moles per liter. So, keeping this as the reference standard, let us go on to understand what is molality. This goes with the unit small m, molal. Is it temperature dependent, temp independent? Does it require a knowledge of molecular weight? Yes, and m is defined as n divided by weight in kgs. And how would you convert weight? Is that you are going to go number of moles divided by volume times density of solution. So, basically this is nothing but molarity divided by the density of solution. The next unit is normality. Normality is given capital N, and this is temperature dependent. Yes, it does require the knowledge of molecular weight and the concept of equivalence. And how does this go? Normality, as we have seen before, is the product of molarity to the number of equivalents. Remember, to define normality, you have to define what reaction you are going to be using the chemical under. The next series of measurements are the parameters are percentages. So, we have mass percent, which goes unitless. Basically, you have percentage weight by weight is how it is defined. You also have percentage volume by volume, then you have percentage weight by volume, mass, volume, only weight by weight is temperature independent, well these two are temperature dependent. None of this require the molecular weight to be known for the chemical that you are working with. Just for weight by weight, one is able to understand. So, let us go weight by weight. It is going to be given by weight of solute in grams divided by weight of solution in grams times 100. I am not going to end up converting this, but we are able to realize that at the denominator you have something similar to molality. I am pretty sure you will be able to sit down and finish how to convert this to the other. It is going to involve densities that go with it, and also conversion entity that comes from grams to kilograms and to liters. Similar would be the others as well. So, the other entity that we saw here was parts per x. So, this could be parts per million or billion. So, this also goes as ppm and ppb, and ppm roughly translates into 1 milligram per 1 liter. On the other hand, ppb goes as 1 microgram per liter. In this case, it is temperature independent to start with, because you have the denominator as the mass of the solution, but however, that does get changed into the volume of solution. So, the temperature dependence here depends upon the denominator that you go. If it is volume, it is going to be dependent. You do not need the knowledge of what is the molecular weight, and of course, this once again goes very close to weight by weight type of a definition, or even weight by volume. So, the conversion would go in such a fashion. There is also the parameter p value or the p function, which is unitless. This is nothing but negative logarithm of concentration of x in molarity. So, there you goes the direct interconversion from molarity to px. Is this temperature dependent? Since molarity is temperature dependent, yes, this is temperature dependent, and also it requires the knowledge of molecular weight. To finish with, we have mole fraction. Mole fraction is also unitless, it is temperature independent. It does require the knowledge of what is the molecular weight of the concerned chemicals, and the interconversion with molarity is not that straightforward, but basically what we are able to understand, the mole fraction of any constituent I is going to be given by the number of moles in I divided by sum of the number of moles of all the entities that are present within the solution. Now that we have seen all the definitions for these different parameters to determine concentration, why do not we go ahead and take up an example in this case. So, let us take an example of 30% weight by volume of methanol in water. Let us take an example of 30% weight by volume of methanol in water and determine what is its molarity, molality, normality, weight percent, definition of weight by weight, volume by volume, or weight by volume. The few parameters that would be required in this case are density of solution. Density of solution is 0.952 grams per cc. Density of methanol is 0.792 grams per cc, and density of water is 0.998 grams per centimeter cube. All these values are at 20 degrees Celsius. So, now to start with, let us convert weight by volume to weight by weight. And how does this go? So, this first implies you have 30 grams of methanol in 100 ml of solution. 100 ml of solution would indicate that what is the mass of solution? This will be equal to density of solution times volume of solution. Density of solution is 0.952 grams per cc times 100 ml. So, that is going to make it 95.2 grams. So, this indicates if 30 grams is methanol, how much of water is present? This is going to be 95.2 minus 30 grams, which is equal to 65.2 grams of water, right. So, now what ends up happening for to determine what is weight by weight, what is the total is 30 grams divided by 95.2 grams times 100 in percentage. This will be equal to 31.5% weight by weight. So, now comes to the next conversion. Let us look at volume by volume. In this case, you are trying to say you have 30 grams of methanol, and in order to understand what is the volume of methanol, you have to take the mass of methanol and divide it by density of methanol. So, this will end up to be 30 grams divided by density of methanol is 0.792 grams per centimeter cube. So, this will be equal to 37.9 ml. So, therefore, the volume by volume is going to be equal to 37.9 in 100 ml. This will be equal to 37.9% volume by volume. So, we are able to understand 30% weight by volume is equal to 31.5% weight by weight is equal to 37.9% volume by volume. So, be very careful when you are expressing your concentration units in percentage. Without the units, it does not make sense. Now, let us move ahead to determine what is the molarity. So, what did we say? 30 grams of MeOH. So, how many moles is this? Number of moles is given by, this is CH3OH, that will be 12 plus 4 plus 16, 32 grams per mole. So, when you have 30 grams divided by 32 grams per mole, this is going to be equal to 0.9375 moles. So, therefore, the molarity will be equal to 0.9375 divided by 0.1 liters, which is going to be 9.375 molar. Moving on, what is the molarity? Molarity is going to be given by 0.9375. As we know, volume is 100 ml and you need to convert it to mass. The mass is going to be given by volume times density. 100 times density was 0.952, that makes it 0.0952. It is going to be equal to 9.847 molal. Now, to understand which reaction we are going to determine normality for, let us take for an example, we are doing combustion of methanol. In combustion of methanol, methanol reacts with oxygen. Let us assume complete combustion. We can also do the normality for incomplete combustion a moment later. Complete combustion will give you carbon dioxide. So, this has to be equal to 3. So, let us make it 3 by 2. So, once you have something like this, the important thing to understand here is that the oxidation number of carbon in this case is 1. On the other hand, it goes to plus 4. Therefore, 3 electrons are involved. For complete combustion, 3 electrons are involved. So, therefore, the normality is going to be given by molarity times 3, 28.125 normal. On the other hand, if we are doing an incomplete combustion, which is CH3OH plus O2 giving carbon monoxide plus H2O, this is already balanced, and here what ends up happening is that oxygen goes to something like a plus 2 oxidation state from plus 1. Here normality will be equal to molarity what one is able to understand here, the normality determination requires the knowledge of what kind of reaction is undergone by methanol to define what is the normality. Okay. So, now we could always define what is the P in methanol, but since the concentration is so high, generally P is determined, generally P value is always associated with lower concentrations of solute. Let us determine what is the mole fraction. We just determined the number of moles of methanol is 0.9375. In this you also have 95.2 grams of water. 95.2 divided by 18 will be number of moles of water, that is going to be equal to 5.29 moles. So, the mole fraction of methanol is going to be equal to 0.9375 divided by 0.9375 plus 5.288. This will be equal to 0.151, and therefore, H2O will be approximately 0.849. So, what we have seen here is that the mole fraction, although you have significant amount of methanol, is actually lower because you are dividing it by the molecular weight, and the remaining is being water, you have significant amount of water that is present. Let us switch a few gears and let us try to understand the stoichiometry a little bit more. Now that we have defined all the different concentration units, let us take a simple reaction of A plus 2B that results in an equilibrium of C plus 3D, where the numbers in front indicate their stoichiometric equivalence. Okay, now that you have something like this, so what we are able to understand here, if you have 1 mole of A, that requires 2 moles of B to give 1 mole of C and 3 moles of D. Now, the question is, this is under the assumption that the reaction goes to completion. For this reaction that has been given here, let us take an example where instead of giving the stoichiometric proportions, you give non-stoichiometric proportions. This many times happens when you are starting out with a reaction being unsure of what are its stoichiometric equivalence. So, for instance, let us say you provided 2 moles of A and 1 mole of B, and then you are trying to ask how much of C is going to be made. Once again, let us assume 100% completion. So, what is going to end up happening here? In this case, the B is going to be the limiting reagent. B is going to be the limiting reagent, and you realize for 2 moles of B, 1 mole of A is going to be required. So, out of this 2 mole, you are only going to end up using 0.5 moles, and since both these 2 moles are going to be used, you are going to make 0.5 moles of C and 1.5 moles of D. This is once again assuming 100% conversion. What could end up happening here is that it does not have to end up in a complete conversion to C and D. It could be in an equilibrium where you form less of C and D. For instance, let us assume 80% conversion happen and you have a 0.4 mole of C. Then can we ask a question, how much of A or B are remaining under such a case? So, as I just mentioned, you started with 2 mole of A and 1 mole of B to get 0.4 mole of C. So, in this case we are talking about 80% completion. So, in that case what ends up happening, you are able to realize 3 equivalents of D is going to be coming up. So, this is going to be 1.2 moles, and on the other hand, if only 0.4 got used up, you are going to have 0.2 moles of B remaining. How did I calculate this? I calculated this as 1 minus 0.4 times 2. The 2 comes from the fact that you have 2 equivalents of B that is required, and 1 is the initial concentration of B that was provided. And out of the 2 moles that you started with, you are going to end up with 2 minus 0.4. So, you are going to have 1.6 moles of A, 0.2 moles of B remaining with 0.4 moles of C, and 1.2 moles of D being prepared. So, what we have seen here is that how does the equilibrium constant change. In this case, of course, you assume complete completion of reaction, where the equilibrium constant would have been given by, in this case it would have been given by, let us say we are going with the mole fraction. The mole fraction indicates it is a k chi that we are trying to calculate, and then the number of moles as a sum, you are going to get something to the order of 1.5 plus 1 plus 2, that is going to be 3.5 moles being the total, and then your k chi is going to be given by chi c to the power 1, chi d to the power 3 divided by chi b to the power 2 and chi a to the power 1, right. So, now this has happened. What is chi c in this case? Chi c is going to be given by 0.5 divided by 3.5. Once again, what I am assuming here, this is the this is the equilibrium constant for the 100% completion. What you are able to realize on the other hand, if you have an 80% completion, the total number of moles is going to be the sum of 1.6 plus 0.2, which is 1.8, plus 0.4 2.2 plus 1.2, that is going to be 3.4 moles. In this case, your chi c is going to be 0.4 over 3.4, but the value of chi c, chi d, chi a and chi b are going to change, which results in a different equilibrium constant. So, basically one has to be a little careful calculating equilibrium constants. Let us try to push this a little bit by using the Le Chatelier's principle. So, in this principle, you know for a fact that if you are adding some of the products, the equilibrium constant is going to be pushed towards the reactants. So, let us write the reaction again. 1A plus 2B gives C plus 3D, and we took the example of having 2 moles here, 1 mole here, nothing of C. Now, let us take for an example, you already had 1 mole of C, sorry, let us assume that you had 1 mole of D that you have already provided. So, what this will end up doing is it is going to push the reaction more towards the reactants. Let us assume that in this case, what you have been able to determine that C is present in 0.3 moles after the reaction gets over, and what you are able to understand here is that this immediately implies you used about 0.6 here. So, you are going to have 0.4 remaining and 1.7 of A remaining, and B is going to be 1 plus 0.3 times 3, because you have 3 equivalents of it, that will be 1.9 moles. Once again, going back, you have a total number of moles which is going to be equal to 1.7 plus 0.4 2.1, 2.4 plus 1.9 is 4.3 moles. Now, chi c is 0.3 by 4.3. What you are able to realize once again in these examples is that the equilibrium constant helps you understand how much of the reaction goes forward, and in these 3 different conditions, where in condition 1 you assumed 100% completion with non-stoichiometric amounts of reactants, and with 80% completion, once again the similar non-stoichiometric amounts, you are able to realize the equilibrium constant defined by k chi is different from one another. Similar is an example where if you also provided a little bit of the product being present, there is a difference that comes in the equilibrium constant that is determined. So, one is able to understand, providing an idea of how much reactants and products you have and the equilibrium constant helps you judge how much forward has the reaction gone. These examples help you understand how stoichiometry works in different chemical reactions under different conditions that have been set up by the researcher. Let us take another example right now, where if the px for a given solute 13.5 units, what is the concentration in molarity? So, px is defined as minus log of concentration of x in molarity. So, therefore, what is going to end up happening? 13.5 is equal to minus log of concentration of x. So, this transpires into minus 13.5 is equal to log of x, and therefore, x is going to be given by 10 power of minus 13.5. So, the concentration of x is going to be given by 3.16 into 10 to the power of minus 14 molar. Generally, these kind of numbers which are coming as the 10 powers to certain numbers will be defined in different ways. For instance, 10 power minus 14 can be written as 10 times 10 power minus 15. So, this would translate to something like 31.6 femtomolar. So, let us take a quick look at these kind of numbers which might end up being extremely helpful for us. So, 10, let us start from larger numbers which we are more comfortable with. So, why do not we put 10 power 0 as the reference that we are starting with. So, this is going to be 1. So, something like 10 power 3 is given the unit kilo. So, that generally that is the one that comes with a capital small k. 10 power 6 comes as mega, that is capital M. 10 power 9 comes as giga, which is capital G. 10 power 12 is tera with a capital T and so on and so forth. Let us go looking at smaller numbers. 10 power minus 1 is given as deci. 10 power minus 2 is given as centi. We are very familiar with decimeter and centimeter. 10 power minus 3 is milli, as in millimeters. 10 power minus 6 then is micro, given the symbol mu. 10 power minus 9 gets the name nano, which goes with a small n. 10 power minus 12 goes with pico with a small p. 10 power minus 15 goes with femto, that is F, that is what we ended up getting in the current example, and 10 power minus 18 is atto, which goes with a small a. There are many other units that would end up coming, but these are the units that we might end up using most commonly and therefore has been introduced in this given example.